Welcome back, and today what we're going to do is we are going over limits at infinity. Students will be able to determine the finite limits at infinity, determine the horizontal asymptotes, if any, and graph the function, and determine infinite limits at infinity. So, let's go. What we're going to start very simple, and we're going to go with a nice, easy exercise. In order to find limits at infinity, first you have to understand what you're actually finding. Now, how do they work? Well, infinity is typically the end behavior of a function. Now, when you speak of limits at infinity, you're talking about the y-axis. So you're going to infinity to the right and negative infinity to the left. So you want to know, what is our graph doing as we approach those points? Now, this is how it works. X approaches what to the left? Well, 0 is the center point, and it approaches negative infinity to the left. Now, how do we get to negative infinity? Well, you start off with small numbers, such as -1, -10, -100. The numbers jump up exponentially, which you should know what exponentially means by now. It means it jumps up by like a power of 10. Like it goes up 9, goes up 90, it goes up 900. Just big jumps. Now, this is our x values. All right? Now, our x values go left to right. Now, what do our y values do when this happens? Well, if you type -1 into that equation, you would type in 3 -1 squared, make sure your -1 is in parentheses, divided by, open parentheses, and open a second set of parentheses, -1 squared, or sorry, -1, close parentheses, squared, plus 1, close your second set of parentheses, and you would get as an answer, I don't know, 3 over 2, 3/2. Now, as x approaches positive infinity, 1, opposites 10, 100. So anyway, I jumped the gun over there. You plug your -1 in, you get -3/2. You plug -10 in there, you get about 2.97. You plug -100 in there, you get 2.997. So what does it look like we're doing as we approach negative infinity? Well, you guys see a pattern? So f of x is approaching, give me the answer, 3. So type these 3 into that equation. Now you don't need to use as many parentheses because they're positive. So 1 in there, you get the same answer. And guess what? You're going to get all the same answers because when you square numbers, they always become positive. So you got 1.5, 2.95, and guess it right? 2.99975. And what is f of x approaching here? It is also approaching the same exact number, 3. So how is that possible? How does it approach 3 on the left and the right? Well, limit at negative infinity is 3. Limit at positive infinity is 3. Remember, limits don't actually reach that number. It's a number they get to right before they get there. So, look at our graph here. This part right here, f of x is approaching what? As we go to the left, as we go to negative infinity, it approaches 3 as x approaches negative infinity. Right here, as we go to the right, f of x approaches, once again, 3 as x approaches, in this case, positive infinity. Now, what can we draw right here to make that make sense? How about a horizontal asymptote? And that's where f of x equals 3. All right, so this graph comes up and it hugs there. It never gets to 3. It never passes 3. It just gets as close as it can. So if we said, and we plugged in like -1 billion, something like that, it would be a ton of 9s and like a 7. All right, and the same thing with positive. Got it? Awesome. That's the concept. So here's the basic rule. Horizontal asymptotes, the line y equals L, is a horizontal asymptote if the graph of f is just the name of the function, if the following is true. So the only way to have a horizontal asymptote is if you do what? The limit equals, from the negative side, as you approach negative infinity, it's L, and then as you approach positive infinity, it is also L. L could be any number there is. Now, what do you notice about these two? They are indeed equal. So there's the rule. If your limits as you approach negative and positive infinity are equal, there is indeed a horizontal asymptote. All right, and you can approach different sides. That's okay, as long as you're approaching the same number. Here's an example. All right, so finding the limit of infinity. So plug infinity in here. 5 minus 2 over infinity squared. Now, infinity squared is indeed infinity. Infinity to the third power is infinity. Square root of infinity is infinity. Remember, we already did a bunch of this stuff before. Now, here's the thing. Do you guys remember what positive or negative infinity divided by any number in the world is? It's just positive or negative infinity because this number is so much bigger than any number. It's infinity. Do you remember what a number divided by infinity is? Just think, type in a number in the calculator, divided by, put as many 9s as you can, hit equal. And that should tell you, you should remember any number over infinity is 0. Any number over negative infinity is 0. Okay? The only thing that matters about this number is the sign, because you got to remember, if there are 2 negative signs, it's a positive. If there's only 1 negative sign, it's a negative. So this becomes 5 minus 2 over infinity is 0. And 5 minus 0 is indeed 5. So the limit as you approach infinity is 5. If I type negative infinity in here, negative infinity squared is also infinity. Your answer would also be 5, and you'd have a horizontal asymptote. So what I'd like you guys to do is try problem number 2 real quick. All right. You should have got the answer. Now problem number 2, the way this works is, if I plug infinity to the top, 2 times infinity minus 1 is infinity, right? 2 times infinity is infinity. Infinity minus any number is infinity. Limit of x plus 1. What's the answer there? That's also infinity. So did you get infinity over infinity as an answer? So what would you think? The answer is probably 1, right? Is that what you got? Yeah? If you got that answer, bad job, you're wrong. Now, that isn't the right way to do it. You guys should hopefully remember you have to use L'Hopital's rule. Now, that's why it's there. You can't solve it this way. You can't just pick up the top, pick up the bottom, and throw infinity in. You have to use L'Hopital's rule. Now, way this rule works, very simple. You choose the what degree parts from the numerator and denominator. Do you remember? Highest degree part. You negate the rest. That means you just erase everything else. Nothing else matters. But those 2 functions. 3. You reduce. And that's the whole concept. So, look right here. I already highlighted the highest degree functions. Constants are obviously the lowest degrees. If you have a variable to a negative power, that's even lower than a constant, so that's even more worthless. So, you want positive numbers. So we're going to pick 2x and x. Now, what could you do with 2x and x? Negate the rest, so we erased all this. Reduce. What reduces out of here? We can take out the x's. So our answer is 2 over well, what do these become? Technically, that becomes a 1. All right? This is 2 times 1 over 1. 2 divided by 1 is 2. So what is the limit of a constant as you approach infinity? Do you guys remember this? This is when we went over limits. So this is chapter 2. So there's no x to plug this in. So the limit of any constant, right, as x approaches any number is just that constant. So our answer is 2. Got it? Pretty simple. Why don't you guys attempt this one? All right, hopefully you got it. Same concept, highest degree, negate, cancel out, and guess what? It doesn't matter that this is negatives because you still can't plug anything in. You have 2 as an answer. Now, let's look at our example right here. This is the actual graph here. Now, what do you notice at this graph? As it approaches infinity here, you're approaching 2 from the bottom. As you approach negative infinity here, you're approaching 2 from the top. And there's a horizontal asymptote that runs around it too, because these are the same. Got it? Pretty simple concept. Hopefully you guys get it. Horizontal asymptotes. All right, we're going to bring this all together very shortly. So here are some three easy rules. The denominator has a higher degree. What do? The numerator and the denominator have the same degree. What do? And if the numerator has a higher degree, what do? So first thing I want you guys to do is I want you to take these problems and I want you to reduce them all using L'Hopital's rule. Got it? Here's a hint. In case you didn't get it, maybe you like some colors to help you out. Oh, let's look at this problem. So we take 2x over 3x squared. When we reduce this, the x comes out, and you take one of the 2 x's left on bottom out, leaving you with a 3x. So you got the limit of 2 over 3x. Simple 8th grade algebra. Now, if I type in infinity there, 2 times over 3 times infinity. Any number times infinity is infinity. And any number divided by infinity is, say it out loud, 0. So the rule for every single time, if the denominator's degree is higher, x squared is higher than x. Okay, if this is x to the 8th, higher than x to the 12th. Nope, x to the 2nd. Okay, if anytime this degree on the bottom is higher, your answer is always going to be 0. All right, because technically you have more infinity powers there. So some weird rule there. Next one. You should have reduced this. 2x squared, 3x squared. Cancel out the x squared, just leaving you with a 2/3. And what did we say before the constant? all right, is just that number, okay? Because there's no x to plug the infinity into. The numerator and denominator have the same degree, then the answer is just a number. That's the only time you actually get a number answer. Every other answer, well, besides 0, technically, is going to be 0, or look at number 5. You can reduce this. 3 on top, 2 on bottom. You take 2 out of each one. So, left with 1 on top. So you got 2x over 3. If I plug infinity into there, what is 2 times infinity? Good, it's infinity over 3. Any number over infinity over any number is infinity. Answer is going to be a positive or negative infinity. All right? So these are the 3 main concepts you need to know. And this is the whole gist of the whole lesson. Very easy lesson today. So I want you guys to go through. We're going to go through some guidelines once again. And we're going to use this to do these 3 problems. So first one says, if the degree of a numerator is blank, the degree of a denominator, the limit of the rational function is what? What is it? The numerator is what the denominator here? Less than. Remember, yell out when I point to you. The denominator and the limit of the rational function is, as we said before, 0. So let's go prove this. Solve this problem. Good. Reduce. You're left with 5 over 10 reduces to 1/2. You're left with 6. X is on bottom. Since you have more x's on bottom, this is less than this. Your answer is indeed 0. Problem B. All right. You take your highest degree terms, 12x cubed and x to the 5th. All right. 12x cubed over x to the 5th equals, where do I have more? Well, if I reduce, I see I have 2 more on bottom. All right. And you get 12 over x squared. Since there is more on bottom, that means your answer is indeed 0. All right. Any questions? Awesome. The degree of the numerator, second rule. So numerator less than denominator, or denominator greater than numerator, answer is 0. If the degree of the numerator now is not less than, but greater than, I went out of order, equal to the degree of the denominator, then the limit of the rational function is the actual value of the fraction. So, when you reduce this, take out the x to the 8th, you're left with 4 over 7. That was pretty easy. Look over here, let's see, highest degree term here is x to the 7th. Highest degree here term is, you have to keep the sign as well, negative 11x to the 7th. So you just pull out these. All this stuff doesn't matter. Only when you're dealing with infinity, with actual numbers, it would matter. All right, so 13x to the 7th, x to the 7th, they cancel out, leaving you with a negative 13 over 11. And that's your answer. See? Not too tough. Now we have it. The degree of the numerator is what? What's 7 compared to 4? But greater than the degree of the denominator. The limit of the rational function is, as we said before, there's your positive or negative infinity. Reduce. You're left with 3x to the 3rd over 10. So the numbers don't matter because they're both positive. So we have x to the 3rd. Now what if this was positive infinity? Well, infinity to the 3rd power is infinity. What if it was negative infinity though? Negative infinity to the 3rd power is 3 negative signs. And since it's on top, your answer would be negative infinity. 2 totally different answers, okay? And what this means is as you approach infinity, your answer would just be going up to infinity. As you approach negative infinity, your answer would be going down to negative infinity. Got it? Awesome. Why don't you guys attempt these 2 problems, 6 and 7. They're fairly simple to do. Remember, you have to reduce the numbers first. So, let's go. You should be done with your problems. So, let's go over the problems. You take the highest degree term, which is 3x. Highest degree term on bottom is square root of 2x squared. All right, now, you can't just get rid of the radical. Okay, so your actually answer is not 2x squared, but the radical of 2x squared. So you keep your 3x on top, and you're just getting rid of this 1 here. Now, square root of 2x squared, you kind of have to split it up, okay? You have the square root of 2 times the square root of x squared. Square root of 2 is 1.41. That doesn't help us because it's just a number. But the square root of x squared is what? It is x. So you end up with 3x over square root of 2 times x. Notice this is not under the radical anymore. This is just an x by itself. Now, because you did that, what you're allowed to do now is you can cancel out the x's, leaving you with 3 over radical 2. Now, that's your answer. So you can write as 3 over radical 2. Or as we did in the previous lesson, you typically don't want radicals on bottom, so you would multiply this by radical 2 over radical 2, and you get 3 radical 2 over 2. Right? Either way is acceptable. This one's the way that's written better. All right, so why don't you try 7? Same problem, just with a negative infinity. This is a trick problem, so a lot of you probably messed up. Let's see who thought outside the box. There's all the rules that apply here that don't make sense. So same reduction, okay, same splitting, all right? We're gonna keep this, radical 2, radical x squared, same exact concept, same exact thing right here, okay? So radical 2x, the x's cancel out, so our limit is pretty much the same. Limit of negative infinity now, 3 over this was limit of positive infinity. Now, here's where our answer is a little different. The answer is 3 over radical 2 is probably what you got, but that's wrong. Now, why would that be wrong? That's what I want you to think of. Do we think? Your answer is actually a negative, not a positive. So why is this negative? Do I just throw the negative on? But no, the reason for that is, even though x is approaching 6, for number 6, x is approaching infinity, and x is approaching negative infinity for number 7, have the same answer. When you cancel everything out, they have different signs. All right? This is a horizontal asymptote on the right side. This is a horizontal asymptote on the left. Now, here's the problem. The reason these are negatives is, look at the sign. If I put negative infinity up here, the top would be a negative, right? If I put negative infinity squared, that becomes positive. A negative over a positive is always going to be a negative. So with negative infinities, you always have to go back into the equation just to get the signs of the numerator and denominators, and then throw that in almost as like a second problem. It's just a little tricky thing to do. All right? Let's try problems 8 and 9. This one's easy. And then I want you also to try to do your graph. Mine's going to look ugly, but it's the best I can do in PowerPoint. So, what's infinity cubed? Well, this is over 1, so it's just infinity. What's this one? Negative infinity to the third power. And as I said before, you have how many infinities? 3. So negative infinity, negative infinity, negative. Negative and negative is a positive. Negative makes it back to a negative. So you have positive infinity and you have negative infinity. Now what that means is, as I'm going to infinity here, my graph is going to be going up. As I go towards negative infinity, my graph is going to be going down. And this is the graph you actually have. Remember, if you know the cubic function graph that we did previously, as you go to positive infinity, as you can see, my graph goes up. As you go towards negative infinity, my graph is going down. All right, this is just to show you pretty much the relationship between the f of x and the x. Hopefully, it makes a little more sense to you. Good? All right, let's look at 10 through 15. Why don't you guys use L'Hopital's rule to solve these problems? Good? All right, let's get going. So, take the highest degree terms, x squared and x cubed. Cancel them. That x squared goes away, you're left with 1x on bottom. So 1 over x, you have a 1 over infinity, 0. Remember, x, any number over infinity or negative infinity, always 0. And that doesn't matter if it's positive or negative either. Here, x squared and x squared, the two highest degree terms. These cancel out and become what? Not 0, but 1 over 1. All right? And 1 divided by 1 is 1. Infinity of a constant, no matter what it approaches, is that constant. Here, you have an x squared and you have an x. These are all easy problems. Cancel. You're left with 1x on top. So limit of infinity over 1, infinity divided by any number, is indeed infinity. All right, these are very easy questions. Hopefully you completed these as well. If you mess these up, retry these problems. Next one, you keep the negative 2x and the positive x cubed. So when you do this, cancel this out. You lose 1x here, you lose one of these 2x's, so you're left with 2 still x's, so you have an x squared still here. Negative 2 over 3x squared. More x's on bottom. So this becomes infinity, and it doesn't matter positive or negative, you just have a 0. 0 is neither negative nor positive, so it's always just 0. Right here, negative 2x, positive 3x. So x and x cancel out, leaving you with a limit of x approaches infinity of negative 2/3, which is negative 2/3. How you doing? Good? Negative 2x squared 3x. And notice they're all similar. We just changed the exponents. Oh, I just changed the exponents. So when you do this one, take out one of these two. Take out the whole one down there. All right. Negative 2x over 3. Put the infinity on top. Now look at negative 2 times infinity. Negative infinity. All right. Over 3 is indeed negative infinity. We all good? Awesome. Let us move on to problem number 16. 17, 18, 19. Go. 16 might get it. All right, so let's look. 4 plus 3 over infinity. 3 over infinity is 0, but you still have the 4. So just 4 plus 0 is 4. Problem 17. 5x squared, x, right? Reduce. Take one of these x's out, leaving you with a 5x over, not 0, but 1. So you type in your negative infinity. 5 times negative infinity is indeed negative infinity. What an easy lesson. Right here, 2 more problems to do for this lesson, then we're going to do a little review problem. What do we do? This does not equal radical x. You just keep that x and you keep that x squared. But this is the square root of x squared. Square root of x squared is x. So x over x reduces to 1. Your answer is, well, this negative infinity here becomes positive. This is negative infinity. So technically you have a negative over a positive. So your answer is not just 1. It is negative over a positive is a negative answer. And that means negative 1 is your answer indeed. All right. So always with negative infinity, check these things as well to make sure that you have the right sign. Trickiest one we have. And this last one's easy. 5x cubed, 10x cubed. 5 divided by 10 is 1/2. The x cubes go away. All right. So limit of 1/2 is 1/2. Got it? That's all you really have to do. Now what we're going to do is we're going to do a quick review of the previous lessons and get you into the big review next time, okay? First thing you have to do is find the extrema. The way to find the extrema is, you guys remember, you have to take the first derivative and then set the problem equal to 0 and undefined. So let's look right here. Way to derive this problem is by using the quotient rule. So f is your numerator. Your numerator here is x. Your denominator is your g, 1 minus x. Derivative of x is 1. Derivative of 1 minus x is negative 1. All right, now what we do here is f prime g, g prime f. So we do 1 times 1 minus x minus g prime f, negative 1 times x over g squared. 1 minus x plus x over 1 minus x squared. Just leave this like this for now. Don't expand it. Negative x plus x is a 1. Right? That equals 0. So it's 1 minus 0 is 1 over 1 minus x squared. And that equals your f prime x. Okay? So you're going to take this. Well, when we set 1 equal to 0, it doesn't work. So that's not a critical point. But then when we set the numerator equal to 0, 1 minus x squared, you get x equals 1. So that is our only critical number. So our intervals are from negative infinity to 1 and from 1 to infinity. Test number between these two, let's pick 0. So you pick 0 as an answer. 1, you plug it into the derivative. 1 over 1 minus 0. 1 over 1 is 1. 1 is a positive number. Positive numbers are increasing. See? Nice and easy. Now let's pick a number here. Let's say we pick 2. 1 over 1 minus 2. 1 minus 2 is negative 1, but when you square it becomes a positive 1. 1 over 1 is 1, and 1 is a positive number. Positive numbers are increasing. So our graph is going to increase, and then it's going to continue to increase. That's interesting. Think that's possible? We'll find out. Now for concavity, this is a back scratcher. For concavity, what you have to do is not find the first derivative, but the second derivative. So you're going to derive this. We still need our quotient rule. So when we do this problem, our f is 1. Our g is 1 minus x, right, squared. Our f prime is, derivative of 1 is 0. Derivative of this, we can't find it unless we use the chain rule. So u is the inside, 1 minus x. F of u is the outer part, which is u squared. 0 minus 1. This becomes 2u. All right? f prime u, oh, the prime should be there, times u prime is -1 times 2u. -1 times 2 is -2, and this is our u. Now just leave that in there for now. Don't expand it because we're going to use it to reduce later. This guy pops over there. Got it? Still have to use our quotient rule. 0 times 1 minus x squared minus -2, 1 minus x times 1. Now, what happens here is you can reduce some of the stuff. Oh, this is actually this squared, so this would be to the 4th power. That's all right. We'll get it later. So, that becomes 1 minus x. This becomes -2 times 1. This becomes 1 minus x to the 3rd power. All right. If I had a chalkboard, I'd write 3 there. This becomes 0. This becomes plus 2. And this becomes 1 minus x, once again, to the 3rd power. All right. 2 over 1 minus x to the 3rd power. All right, so that's your answer. Now what we have to do here is something very simple. We set the numerator equal to 0. 2 never equals 0. So that is not true. There's no inflection point there. 1 minus x, or 1 minus x cubed, we set that equal to 0. If this was cubed, we just cubed root 0. It would be 0 anyway, so this is like the 2nd step. Add x to both sides and x equals 1. Notice it's the same as this one, which is okay. So, same exact intervals. You can pick the same test numbers, f of 0. Now, when you take 0, you don't plug it into there or there, you plug it into here. So it's 2 over 1 minus 0, and that equals 2. 2 is a positive number, so that's concave up. Pick a number here. We pick 2 again. So plug 2 in here. 2 over 1 minus 2. Well, 1 minus 2 is -1. 2 divided by -1 is -2. Boom. Negative numbers is a negative, so it's concave down. All right, so we got increasing, decreasing, and we got the concavity. Awesome. Almost put everything together. Remember x and y intercepts? Find x-intercepts, you set y equal to 0. So when y equals 0, how do we make this 0? So it'd be 0, right? Can't ever make the bottom 0, so it's just when the numerator is 0. That's x equals 0. To find the y-intercepts, you set x equal to 0. 0 over 1 is, there we go, also 0. Got it? Colors are backwards. This one, asymptotes. Well, the only asymptote is when the numerator, or sorry, the denominator equals 0. So that's when x equals 1. All right, so if you got all that stuff right, you're awesome. Now, you want to see what this actually looks like? What this actually looks like is this graph right here. Anytime I want to check something, I jump on Desmos real quick. As you can see, there is a asymptote going right here, and that is -1. Or sorry, +1, like we said. There's also a horizontal asymptote right here, and this is also at -1. The way we could have found this, I just ran out of space, is if we set the limit equal to positive and negative infinity. So when we do that, we use L'Hopital's rule. We would keep these two. We'd have x over negative x. And that would reduce and reduce to 1 over -1 or -1. So as you can see, the horizontal asymptote is indeed at -1. Notice the graph is increasing before you get to 1. And after you get to 1, it's still increasing. Also notice there's a concavity of going up. You can put the water and hold here on this part. And the concavity is down afterwards. So everything we said did hold true. All right, so hopefully you get this. And if you don't, we're going to spend about 5 days going over the review. All right, the review is going to be, we're just going to keep on busting it out and buttoning out. You guys are going to eventually be able to graph all these. This is one of the harder ones. There's polynomials, and there are also quotients, rational numbers. So hopefully you'll be good. All right, take care and have a good day. Hopefully you learn limits at infinity.